Black holes are among the most mysterious and fascinating objects in the universe. These cosmic phenomena, where gravity is so intense that not even light can escape, challenge our understanding of space, time, and the laws of physics. In this video, we will explore black holes from their birth to their eventual death, examining how they form, how they evolve, and what ultimately becomes of them. The story of a black hole begins with a star. Stars are massive balls of gas, primarily hydrogen, that generate energy through nuclear fusion. For most of a star's life, a balance exists between the inward pull of gravity and the outward pressure from fusion reactions. However, when a massive star, typically one with at least 20 times the mass of our Sun, exhausts its nuclear fuel, it can no longer resist the force of gravity. As fusion ceases, the core collapses under its own weight. If the core's mass is sufficiently large, usually more than about 2.5 solar masses, it collapses beyond the neutron star stage, forming a black hole. This collapse happens so violently and rapidly that a region of space becomes infinitely dense, a singularity, surrounded by an event horizon, the point beyond which nothing can return. There are three main types of black holes. 1. Stellar mass black holes, formed from the collapse of massive stars. 2. Intermediate mass black holes, hypothetical black holes with masses between stellar and supermassive types. 3. Supermassive black holes, found at the centers of galaxies, with millions to billions of times the mass of the Sun. Structure of a black hole. A black hole is not just an empty space or a hole, but a region defined by physical properties. Singularity, the core, where mass is concentrated into a single point of infinite density. Event horizon, the boundary around the singularity where escape velocity equals the speed of light. Once something crosses this limit, it cannot escape. Accretion disk, often found around actively feeding black holes, it's a disk of gas, dust, and stellar debris heated to extreme temperatures by gravitational energy as it spirals inward. Black holes do not suck matter like a vacuum. Instead, they exert gravitational pull like any other massive object. An object orbiting a black hole at a safe distance would remain in orbit just as it would around any star. Growth and evolution. Once formed, black holes can grow by absorbing surrounding matter and merging with other black holes. Matter falling into a black hole contributes to its mass and can emit massive amounts of radiation during the accretion process, making some black holes the brightest objects in the universe known as quasars. Supermassive black holes grow over billions of years and are found at the centers of most galaxies, including our Milky Way. Their origins are still debated. Some theories suggest they formed from the direct collapse of massive gas clouds in the early universe or from mergers of many stellar mass black holes. Black holes can also merge with other black holes, a process that releases gravitational waves, ripples in space-time first detected in 2015 by LIGO. These mergers provide valuable information about black hole masses, spins, and formation history. What happens inside a black hole? The interior of a black hole remains one of the greatest mysteries in astrophysics. The singularity, as predicted by Einstein's general theory of relativity, is a point where density becomes infinite, and our current laws of physics break down. Quantum mechanics, which governs the very small, and general relativity, which governs the very large, both fail to fully explain conditions inside the singularity. Physicists believe a quantum theory of gravity, perhaps in the form of string theory or loop quantum gravity, may eventually resolve these contradictions. Until then, the inside of a black hole remains a realm of speculation and theoretical exploration. Hawking radiation and black hole evaporation. In 1974, physicist Stephen Hawking proposed a groundbreaking idea: black holes are not entirely black. Due to quantum effects near the event horizon, they emit a faint glow known as Hawking radiation. This radiation is caused by particle-antiparticle pairs that spontaneously appear near the event horizon. One particle falls in, while the other escapes, making it appear as if the black hole is losing mass. Over incredibly long periods, far longer than the age of the universe, this radiation causes black holes to lose energy and shrink. Eventually, a black hole could evaporate entirely in a final burst of radiation. This process is extremely slow for large black holes. A black hole with the mass of the Sun would take about 10·67 years to evaporate. The death of a black hole. Black holes are not eternal. According to the theory of Hawking radiation, they will gradually shrink and lose mass until they eventually vanish. The final stages of evaporation are still poorly understood, but it's believed that the black hole would release a massive burst of energy, perhaps equivalent to a thermonuclear explosion, in its last moments. This final burst may scatter the remaining information the black hole contained, raising a deep puzzle known as the information paradox. If information about matter and energy is truly lost in a black hole, it would violate the principles of quantum mechanics. Some physicists suggest the information is encoded in the Hawking radiation or stored at the event horizon in a theoretical structure called a firewall. Others propose that black holes might leave behind a stable remnant. Black holes are far more than just cosmic oddities. They are windows into the most extreme physics in the universe. From their violent birth in the collapse of massive stars to their slow evaporation through Hawking radiation, black holes tell us about the nature of gravity, quantum mechanics, and the ultimate fate of matter and energy. Their study continues to inspire new scientific discoveries, including gravitational wave astronomy and deep space imaging like the Event Horizon Telescope's image of the black hole in M87. Though much remains unknown, black holes may one day help us unlock the deepest secrets of the cosmos, and of space and time itself.